Yes, hello guys, welcome back. I'm your friend InSaxO. Today we are going to learn the deep deterministic policy gradients. What a long term name. But don't worry, it won't be that hard. Let's get into the Colab. Yeah, let's get started. Deep deterministic policy gradients is a model free of policy algorithm for learning continuous actions. Well, it's very important to understand the continuous actions. In the previous videos, I'm pretty sure that I have covered some non-continuous reinforcement learning algorithms, and for that case we have some certain actions, for example either 1 or 2 or 3, 4, 5, that's some certain numbers. But for now, for this case, what the word continuous mean is that it have an infinite actions ranging from -2 to +2. So in other words, instead of producing the integers, we are going to produce some float numbers. Right, let me just read those sentences for you. It combines ideas from DPG, deterministic policy gradients, and DQN, deep Q network. It uses experience, replay, and slow learning target networks from the DQN, and it is based on DPG, which can operate over continuous action spaces. Problem: we're trying to solve the classic inverted pendulum control problem. This is just a game, and we can head into here. This is how the game looks like. We just got a stack, and our goal is to let it hold still vertically. In this setting, we can take only 2 actions: swing left or swinging right. What makes this problem challenging for a Q learning algorithm is that actions are continuous instead of being deseparate. That is, instead of using 2 separate actions like -1 or +1, we have to select from infinite actions ranging from -2 to +2. Quick theory, just like the actor-critic method, we have 2 networks. One, the actor, it proposes an action giving a state. In other words, it takes actions when a certain condition reached. And another one is critic. It predicts if the action is good or bad by giving a state and an action. So this is the predictor, and this one is the executor. This one thinks about the future. This one thinks about the current action or execute the current action. DDPG uses 2 more techniques not present in the original DQN, deep Q network. First, it uses 2 target networks. Why? Because it adds stability to training. In short, we are learning from estimated targets, and target networks are updated slowly, hence keeping our estimated targets stable conceptually. This is like saying, I have an idea of how to play this well. I'm going to try it out for a bit until I find something better, as opposed to saying, I'm going to relearn how to play this entire game after every move. Yeah, I think this sentence is quite bad because from my previous experience, if you do this kind of thing, you probably will never learn stuff because you may fail at some point, and if you fail, you're gonna learn it from the zero. So it's kind of time wasting. You don't have to do that. You just have to, always try to find something better to learn. Second, it uses experience replay. Well, this is very important because if you replay your experience, you don't have to go through the game again and again. You just have to replay what you been through. Waystone last of tuples, state action reward next state. And instead of learning only from the recent experience, we learn from sampling all of our experience accumulated so far. That's good. Now we'll say how this is implemented. First, we're gonna import the gem, import the TensorFlow STF, import the carriers from, import the layers from the carriers, and import the NumPy, import the Matplotlib. This is for the graph printing. Okay, let's write anyway. Then we're gonna say the game that we're going to play is have a LAN, which is this one, Paginal version 0, and we use GYN to make such a game to get the environment of that game. Then we say we're gonna get the observation space, get the number of states. Oh, first let me run this quickly. So the size of the state space is 3, and the actions, all those actions that we can take is just 1. Maybe it's just a float number, I don't know. And the upper bound, what is that? The space height is 2. Oh, action space height. Alright, so that means this number, the actions that we can take for it has a maximum value, which is 2, and it also has a lowest value, which is -2. So as I said before, for this game we only get 1 action, and that action is a float. It's a float ranging from -2 to +2. To implement better exploration by the actor network, we use noise. What is this word mean?
Perturbations.
To implement better exploration by the actor network, we use noise perturbations, especially in whatever process for generating noise. As described in the paper, it samples noise from the correlated normal distribution. Yeah, what is that? I don't know. Anyway, it's just a class to implement some noise. And for this kind of thing, as you know, it's totally about mathematics. So even if you know every part of that code in a grammar level, I mean, you know every operations, what it does, but in the end, if you look at the whole expression, you don't know what's happening there. So that's how mathematics works in the coder's world. Once you involve it, it's no longer just codes, it's also mathematics. Okay, let's forget about that and just run it. And here we go. This is the corresponding mathematics representation, and as you can see, it's quite hard to understand. Mean squared error of y minus whatever QSA, where y is the expected return as seen by the target network, and QSA is action value predicted by the critic network. Y is a moving target that the critic model tries to achieve. We make this target stable by updating the target model slowly. Actor loss, this is computed using the mean of the value given by the critic network. For the actions taken by the actor network, we seek to maximize this quantity. Maximize. Should we minimize the loss? Hence, we update the actor network so that it produces actions that get the maximum predicted value as seen by the critic for a given state. Anyway, this let's say here we get a bunch of code. Let's run it first. Let's first read about how what kind of thing those codes does. Here we define the actor and critic networks. These are basic dense models with ReLU activation. We need the initialization for last layer of the actor to be between this number and this number. This prevents us from getting 1 and -1 output values in the initial stages, which would scratch all gradients to 0 as we use TIN activation, TNH. Okay, here's the buffer class. It takes the buffer capability and page size. To my understanding, I guess this class is used to save some data, save some historical data. And for the update function, it would take the state, reward, action, negative states, and by using those arguments, it's gonna do some calculation to get the loss, I guess. Yeah, here we go. It did some calculation to get the loss, and let's say even to do the gradient kind of stuff to actually train the model. Yes, as I think, here we go. It trains the actor model, and it also trains the critic model. Okay, then let's get into the next one, because I really do not want to go into detail with those things, because it's probably not necessary. And then what it does is to define two functions. Get actor. This is the model structure, the real model structure. It defines the input layer with a shape of state. So in other words, the actor will take the states as an input, and by going through two dense layers, it gets the final one result, and I guess that's the action. And it should be here we go. The output has to times the maximum value. So in the end, we probably would get the value from -2 to +2. And again, for the critic kind of stuff, it also takes the state as the input and by going through two dense layer and also combined with the action kind of stuff, in the end it concatenates the state layer with the action layer to get a new layer called concatenate layer. And for this one, we'll relay on the concatenated layer to produce the final result, which is the float number. And in the end, we return this model. And then we can do a review about the actor. The actor takes the state as the input and output the action. And the critic model, it takes the state and the action as input, as I said. As we know, that is the main job for the critic is to do a prediction about how good the state and the action combination works. So in the end, this output should be the predicted reward. Yeah, I think that's correct. Policy returns an action sampled from our actor network plus some noise for exploration. So, yeah, as I think, the actor will output the actions by giving it a state as an input. The actor will return the actions that he thinks it's best to execute. So the policy for this function, what it does is to, instead of directly get the action from the actor, it adds some noises. In other words, it adds some readiness into the final action. Why we do that? Because we want to do some explorations. And in another word, if you want to do some explorations, you do not do things normally. You'll do something that's different than anyone else, because if you do things like anyone else, you can never find something new. If you want to find something new, you have to do things differently. Okay, so let's run this function and go on. What is this? Training hyperparameters. So those lines of code defines the hyperparameters. In other words, it's just some parameters. So in the real life or in the real training, we will often change those values to try to get a better result. But if you have a good machine or if you have a super computer, you could write a script to automatically test those numbers, to automatically change those numbers. Here we go. Now we implement our main training loop and iterate over episodes. We sample actions using policy and train with null at each time step, along with updating the target networks at a rate of TAU. Here's the rate, the learning rate, I guess. And for this one, this is a training loop. It will go through from 0 to the total episodes, which is 100. So it's gonna run 100 times. Okay, so let's do the training here. Yeah, as you could say, the training was getting started. The average reward from this number to this number, and then generally goes down. For now, the reward is negative. It's a negative value, and that's not correct. To be honest, the reward should be always a positive number, or in other words, it must be a positive number. Otherwise, that won't be called the it won't be in other words, the reward should always be positive, otherwise it would be called a punishment. The good news is that as the episode goes up, as we train more and more times, the awards is getting bigger and bigger. That's a good thing to see. Now it almost reaches the end, and to be honest, it's finished after 100 of episode training. And here's the result: as the episode goes up, the average reward also goes up from negative 1000 it goes to the negative 200. If training processes correctly, the average episode daily reward will decrease with time. Yeah, feel free to try different learning rates, TAU values, and architectures for the actor and the critical networks. The inverted problem has no complexity, but DDPG work great on many other problems. Another great environment to try this on is never landing continuously too, but it will take more episodes to obtain good results. Anyway, let's just save the weights. It's very important to save the weights every time after your training, because the weights contains the training state. If you do not save it, you'll lose all your training. You know what? I found a problem for this notebook. It only covers the model constructing and weight saving, but it didn't cover how can you actually use your model to play this game. That's bad. Okay, now I understand why they didn't cover that part of code. Well, it basically because the Colab doesn't support to do the display from the GYN. In other words, if you render the environment from the GYN in the Colab, you'll get an error and it will say land base is not defined. So for the Colab, you can only save your, you can only do the training kind of stuff. You won't be able to use it to work with the GYN directly. So the only thing you could do is to first do the training, then save your rates. After that, you can go to the files and download your files one by one. So in the end, you could just use this model on your local machine. And again, you could also download this chapter notebook to your local also. Hello guys, welcome back. You know what, though we couldn't be able to run the GYN on the Colab, but we could run it in our local system. And what I did here is to download all those weights to our local, and I want to run the software right in my local machine. So what I did here is to create the play and import those packages. Although I do not have a GPU, but I could install the CPU version of TensorFlow, and I indeed run all those kind of stuffs. I guess we do not need this. Okay, then I got the actor by defining the model, and in the end I want to set the weights with the weights that I downloaded from the server. And then I got an error. It says that we cannot import that because it has a different layer structure, and it's quite weird. I don't know why that would happen. So I changed my method. Instead of saving the weights, I just saved the model entirely to a H5 file, and then I downloaded both of them. So now I have both of those models. Then I could use it to actually run our game, I guess. So at the first, I imported those necessary packages. Then I defined the environment, which is the game environment. Then I loaded that model from the H5 file, which is the actor. This is a model that we're gonna use to decide which actions to take on each different state. And here I created a loop, but it's not necessary. We could also set it to true to let it run forever. For example, we could say while true. Okay, then at this beginning, I resetted the environment. By doing that, we get the initial state, which is an image. Then by converting that state into a tensor, we pass by that state into our policy, which is this function. And inside of that function, what I did is to call the actor model for the state to get the result from this model, and we scratch it, probably convert it. It's a command or it's a function to convert the multiple dimension vector into one-dimensional vector. I guess that's a functionality for that function. And then we make sure that the result we make sure that result set it in between the negative 2 and positive 2. Then we return that action result. And here's the final action that we get. Then I call the environment step to let the environment take that action. So in this case, it will return us a new state and the reward we got by making that action, and also whether our game has been done or not. And we do a rendering, which is to show that environment on our screen. And you will see that later when I run this script. And if the game was over, then we print out the message of game over, and we break this loop, and we reset that environment to start a new playing. Now, enough explanation. Let's just run this code. And here you go. This is what you say of the game and how the machine learning or how our machine was playing this game. And you will say the result is quite bad and it's keeping game over. It's keeping doing that. So now you probably already understood what the render function does. What it does is to render each image or each step in to our screen so that you could see a window like this. Okay, I guess the only problem for this, why we get such a bad result, is that we haven't trained enough yet, because in the end we get a negative reward. That's totally bad. I guess it should be a positive reward. So I'm gonna increase the episodes from 100 to maybe 200. So I'm gonna do that training again. Hello guys, welcome back. Now I finally solved the problem that we got. Yeah, it's why we get the bad results before. Yeah, it's simply because I didn't update the state. So for each time whenever we have taken an action to our environments, we'll get a new state, and we need to make sure to update the previous state equal to state, so that for the next time we will feed a new state or new environment image to our model, so our actor model could do a prediction based on that new environment image. So if we do it in this case and we run this model again, we would say this model perfectly fit into the center and it will last for a while, and that's exactly what we want to achieve. So not bad. And we can even add some readiness to it. If you want to do that, it can be as simple as say lampy reading.reading less than 0.1. If that's true, we add some readiness to it. So it will look like this, and it's probably the same thing, but it will add more readiness to it. But we only need the readiness in the training part. We do not need it in the real in the production time. So that's today's tutorial, and inside of this tutorial we have learned about how to do the reinforcement learning with the actor critic method, along with there's an and with deep deterministic policy gradients, although I don't know what he was talking about, but at least we have learned how can we do that kind of training with the actor critic method, and that's very important if we want to do some reinforcement learning. And here's also a good thing for us, that is, even if we don't have a GPU and we couldn't train our model in our local machine, but we could train that model at the Colab, and we could download the trained model from the Colab. Then we could use that model right in our local machine, even if our local machine doesn't have a GPU. And as you could say, the result is pretty good. So that's even if we only have a GPU, we could still make some fun with the machine learning. So that's great. So in the next week on the Saturday, maybe I'll do some more experiments on the reinforcement learning. Maybe we will use it to play the Mario again to say if we could make it better. Okay, that's today's tutorial, and I'll see you guys in the next one. Bye!